Thank you very much for the invitation. It's a pleasure to talk in a Friday Fish seminar. And also thank you very much for organizing this. I think it's one of the positive, well, not many positive aspects of this crisis is that we can all attend online talks now. So I've chosen, I will talk about, I guess it's mostly about idea systems, in fact, but I've chosen this topic because I think it's accessible to a wide audience. And if you have already heard me talking about it, it's not that bad because this time I'm trying to come from the point of view of the Atiyah class. So I want to use idea systems to explain or give a geometric interpretation of the Atiyah class of a Lie pair. So I'm going to start with a very basic construction that you might know. It's the bot connection associated to a Lie pair or associated to a foliation on a manifold. And I'll explain it from a very geometric point of view, and then I'll be able to tell you what I want to address in this talk. And then I'll define those infinitesimal ideas. I'll motivate them with holomorphic Lie algebroids, because at the end of the day, holomorphic Lie algebroids are just special ideas in complex Lie algebroids. And then I'll give you the definition, of course. There will probably not be enough time, but if there's time, I might talk about foliated principal bundles, which are a nice class of examples as well. And then I'll give you this obstruction, so this one result, which is actually really easy to prove when you have the objects. Right, so the bot connection. I'm going to assume that you all know at least roughly what a Lie algebroid is. And so we're going to consider such a Lie algebroid. A is always going to be a Lie algebroid together with a subalgebroid. So J will always be a subalgebroid. And the pair AJ is going to be called a Lie pair. So it's very simple. A Lie pair is just a Lie algebroid with a subalgebroid. And the subalgebroid, obviously, is itself a Lie algebroid over the manifold M. And it's always represented on its normal bundle in A. So it's always represented on A mod J by the bot connection, which is basically just a Lie algebroid bracket. So you take a section J, a section of J, and any section A of A, and you take, when I write A bar, is the class of A in A mod J, and then you just define the covariant derivative with the action of J on A bar to be the Lie algebroid bracket of J with A, and then the class of that in A mod J. And that's well defined because if you change your representative A of the class of A, well, you're going to change it by a section of J, and because J is a subalgebroid, then this modification is going to be killed by taking the class of the bracket. Then you can check that the Leibniz condition in the first entry of your bracket is killed as well by taking this class, taking the class and the quotient A mod J. And so you get that this map is the infinity M linear in the first argument. And in the second argument, the Leibniz condition for the Lie algebroid structure just becomes a Leibniz condition for this derivation property in the second argument. So you have a connection, and then it's really easy to check that it's flat because the flatness is just the Jacobi identity. Flatness is the Jacobi identity if you write nabla J of J1, J2, And the class of an A is just the Jacobiator on J1, J2A, well, which vanishes obviously, and the class of that vanishes as well, of course. So you get flatness right away. Right, it's a very easy construction, which is now, I think, standard. But so that you really get that construction, I'm going to give you a couple of examples just to make sure. So if A is a Lie algebroid over a point, so then A is Lie algebra, right? A Lie algebra, which we will call G, and J a subalgebra, let's call it H. Then this map is just the adjoint action of well, G on G, which restricts to an action of H on G, and because it preserves H, you can quotient H out. So you get a new representation of H on D mod H, right? So in that case, it's just that, and we can note right away that if H is an ideal in G, and just to set the notation, I'm going to write ideals little e, little I, but maybe we will not come to those, doesn't matter. So if H is an ideal, then, well, obviously this restricted adjoint action is 0, right? Because I is going to bracket the whole of G into I. So when you take the class in the second argument, you'll have 0. So nabla I, which is this add, is 0. And more generally, we can consider what's called ideal in a Lie algebroid in the literature. So if you take an ideal in A, so we replace J, the subalgebroid, by an ideal, which I'm going to call now a naive ideal. So naive ideal, what is that? It's just the set of sections of I is an ideal in the Lie algebra of sections of A, right? So let's write that. Gamma I, gamma A is in gamma I. Then this dot connection is also 0, right? Obviously, because everything is bracketed into what you killed in A mod I. Then that's 0. And by the way, I mean, it's not very important here, but that forces the anchor to vanish on I. So if before you didn't think it's very restrictive, now you should know and think, and a naive ideal is really naive because it's super restrictive. The anchor needs to vanish on the whole of the subalgebroid. Okay, so those are easy examples to understand maybe the construction. The classical, the classical example, or I guess the motivating example, the one that Bott studied when he defined the Bott connection in the late 60s, is the case where A is Tm, the tangent of a manifold, and then J is an involutive subbundle of Tm, a subalgebroid. I'm going to abuse a bit the language, the notation, say it's a foliation. Then the Bott connection, I write it again, is really defined in the same manner. But here we can understand what it really tells us. So again, the bracket is just a Lie bracket. But in that case, we can think a bit further about it for now. Namely, well, I said F is a foliation, and I mean that. So an involutive subbundle of Tm, you can always integrate to a foliation, which is a partition of your manifold into leaves. So immersed submanifolds that fit well together and all have the same dimension because F is assumed to be regular. And if you identify points that live on the same leaf of your foliation, you get an equivalence relation and you get a quotient manifold, the space of leaves of the foliation. So locally, or I guess ideally, your foliation will look like that. And then you will have a quotient. And if you're lucky, so if F is simple, then this quotient, which I call N mod F, is again a manifold. And then you have a projection, which is a surjective submersion, and yeah, you have nice geometry. So let's call the quotient M bar. Then we go back to the bot connection and we think further about it. So let's take Y, a vector field on M, that is nabla F flat. So you might say, again, there's a little abuse of notation. Actually, it's the class of Y in T M mod F, which I can ask to be flat, but that's okay. It's okay to just say that Y is nabla flat. By definition, it's the same as asking that for any section X of F, the bracket of X with Y is again in F, right? So that this the class of this bracket in T M mod F vanishes, right? So by definition, it's equivalent to saying that Y brackets the whole of all the sections of F into sections of F. And then if you think about it, either you look at that condition in local coordinates, so in adapted charts to your foliation, or you think about flows. Maybe with flows, it's easier to say. So the flow of the vector field Y must preserve the involutive subbundle F. And so that means that it's going to preserve the leaves of the foliation, and that means that it's going to project to a flow on M bar. And that means that we'll have a vector field on M bar that will be pi related to Y. And you can make sense, as I said, of that locally or globally. In any case, you're going to find a vector field on your quotient such that Y is pi related to Y tilde. And then suddenly the bot connection is very geometric, very intuitive. It's a map telling you which vector fields on M project to vector fields on M bar, right? And in a sense, it controls the whole tangent bundle of M bar because you know all vector fields on M bar. They are just a flat vector fields relative to the bot connection. Right, and then obviously that was in the ideal case where F was simple, which in general is not given, right? I mean, in general, this quotient is not a manifold, but still, if it's not a manifold, we can still understand those flat vector fields are the ones that would project. I mean, that somehow know the geometry of this quotient. That's really the idea you should keep in mind. And also, somehow, what should be noted here is that we understand now foliation not only as a subalgebroid of TM, but really as a reduction data, and really as an ideal structure in the algebroid. Why? Because if you look at this condition here, Y brackets the whole of F, the sections of F into F, that's really an ideal condition, right? We cannot write it for all sections Y of TM, but the flat sections satisfy this this ideal condition that we would like for, I mean, that we have in the case of an ideal in a Lie algebra. So we note that, and we also note something else. Namely, if Y1 and Y2 are both nabla J flat, then, well, if the quotient manifold exists, it's really obvious because projectible vector fields bracket to projectible vector fields. I mean, that's standard. But even if not, it's really an easy computation to check that the bracket is always, again, flat. Why? It's again Jacobi. So you just compute for x section of f, nabla x, sorry, of y1, y2, f. By definition, it's the bracket of x with y1, y2, and the class of that. And then by Jacobi, that's x with y1 with y2 plus y1 x with y2. And then we remember this ideal condition I was mentioning. So y1 is nabla, but sorry, here that was an f. y1 is flat. So y1 brackets f into f. So that's a section of f. And y2 is flat. So it brackets again f into f. So that's a section of f. And if you take if you quotient, that doesn't look very good, but if you quotient by f, then you get that this is 0. So that's geometrically clear if the quotient manifold exists, but it's also just clear, it's just Jacobi otherwise. Okay, so let's move on. We go back to a general Lie pair, A and J. I want to tell you what this Atiyah class is before we go on. So first of all, the Atiyah class of the Lie pair, it's a cohomology class in the first cohomology of J with values in this larger space, Hom, A mod J, and A mod J. Obviously, J is represented on A mod J, so it's represented on this whole space. And so we have a cohomology. And I'm going to tell you how this class is defined, but the idea is if it vanishes, then we can find an extension, nabla, so an A connection on A, an extension of nabla J that sends flat sections to flat sections. So if A and B sections of A are nabla J flat, then the connection nabla AB is again nabla J flat. So I'm going to tell you in a bit what an extension is. For now, I mean, it's just think about the obvious extension. You just extend your connection to the whole of A. That condition means that nabla is transversal. Or maybe I'm going to write it below. So nabla is transversal to nabla J, but a priori in this general setting, AJ doesn't tell us that much somehow. I mean, it's not clear what it means. Again, to get a good intuition of what this means, let's take A is Tm and J is F, and let's say that again F is simple. In that case, again X, Y, nabla F flat means XY reducible, or I would say, I said projectible to this quotient manifold. And we ask for nabla XY to be projectible again. So in a sense, we ask for the connection nabla to project to a connection on M bar, right? So a connection that is transversal to our reduction data, which is really nabla F, so to our symmetry, is just a connection that projects to the quotient manifold. So it projects to a connection nabla bar on this quotient manifold. And again, if this quotient manifold doesn't exist, you can still make sense of this transversality, of course. But what I should say in this special setting, when the foliation, when A is just a tangent of a manifold and your subalgebroid is simple, you can always construct a projectable connection, right? You take any connection on the base manifold, you'll be able to lift it because you have a surjective submersion, and that's so nice that you can just construct a connection on M that will project to your connection on M bar, and it will automatically have to be adapted to your reduction data, to your bot connection. So in a sense, we see right away in this particular context of tangent bundles, the Atiyah class is really an obstruction to a foliation being simple, right? If the Atiyah class doesn't vanish, because in that case, I didn't say, but in that case, it's really if and only if here. If the Atiyah class doesn't vanish, then your foliation is not simple. There's no quotient manifold. But the goal of the talk is to explain more generally what the Atiyah class of a Lie pair can tell us in a similar manner. Right. So I'm going to tell you how this Atiyah class is defined, and show a bit this statement here. And then I'm going to relate it to Atiyah's Atiyah class of a holomorphic vector bundle. So here, let's construct the Atiyah class. So first of all, this extension. So you take, and that always works, you take nabla, on A, sections of A, section of A that extends nabla J. So what does it mean? It means that nabla AJ is a section of J for all sections A of A and J of J. So nabla preserves J in a second argument. And then when you construct the quotient connection, because now you can do that, you can construct an A connection on A mod J, because your connection preserves J. This has to be the bot connection when you restrict it on sections of J in the first argument. Maybe I'm going to write it in a more easy manner. So it does nabla J A bar is nabla J A bar on sections of J. So it's really an extension of your bot connection to an A connection on A mod J, and then somehow you lift it. And that's really easy to do to an A connection on A. So you take such a connection, and then just to get an idea, this condition, this transversality condition, we can write it as follows. So for all J in gamma, let's take A, B, nabla J flat, and what we want is that the nabla AB, is there a question? No. Nabla AB, yeah.
Could I ask about the first point? So the nabla is an A connection on A?
Yeah.
Is it easy to see why you can always find this extension?
Well, first of all, you can, right. So you can identify A with A mod J plus J. You take a splitting, right? And then you take any connection on J, any A connection on J. That exists because you can take any TM connection on J and then pull it back with the anchor. And then you just paste them together to an A connection on A. It's going to preserve J by construction. And then the quotient is going to be, we go backwards. We start with the bot connection. We can extend it to an A connection on A mod J by by choosing a complement to J and A. That's always possible. And then that we paste, we combine with any A connection on J.
So how does when you pick a complement to J and A, how does that give an A connection?
You pick right, so you take J, A is J plus, I don't know, K. And then you take any A connection on A mod J, but you're just going to, so you take nabla 1, an A connection on A mod J, and then you're going to write nabla bar of J plus K of a class A. You're going to write as nabla 1 K A bar plus nabla bot. So that's the first extension that works. You just extend your J connection to an A connection, which obviously is not flat anymore. And then you choose a splitting of A as A mod J plus J. And then you combine the whole thing. You combine this connection bar with any A connection on J. So then your combination is going to preserve J, and the quotient is going to be nabla bar, and it's going to be fine, right? Okay. Yeah, that's good. It's quite central. So maybe I'm just going to leave that actually. Yeah. Okay. So now our transversality condition, we want that for all J in J, nabla J of this nabla A B bar is 0, right? Because we want this nabla to be 0 again. So we have, we write this again. It's just nabla JJ of nabla bar AB, and actually I can even write it again as nabla J bar, nabla bar A B bar, and then I can just add 2 zeros to that, namely nabla A bar, nabla J bar, B bar. Why? Because that's 0, because B is nabla J flat, right? And I can also add that term, because again, it's 0, because A is nabla flat, so it brackets J into J, so that's a section of J, and the connection is then nabla bot, nabla J, and then that's 0 again. So really, it doesn't change anything to add those two terms, because I was talking about A and B flat sections. Right, so what do we get? We get the curvature of nabla bar on J, A, B bar, and now we change our point of view and we say, well, let's consider this form. So let's take our extension and let's define omega nabla as a one form on J with values in the homomorphisms that send A mod J to endomorphisms of A mod J. Maybe I should write it with tensors, but okay. So we define, it's just this part of the curvature that we have here. So omega nabla of J is going to eat the class of an A and the class of a B in a second step. And we just define that to be R nabla bar of J A on the class of B. And then there's a little subtlety here. Here I had a class, here I have a representative, but that's okay because R nabla bar on sections of J is the curvature of the bot connection, so it's 0. So that's well defined. And it's easy to check then that it's closed under the covariant derivative, on the nabla J, under the bot connection. So we define the cohomology class, which is this Atiyah class. And actually, I realized I really needed on only this extension. It's for other matters that you need an extension to A. But in any case, we get this class, which is now in the first cohomology, etc. And it doesn't depend on the choice of the extension. So it's this Atiyah class. And then if this Atiyah class vanishes, so if alpha j is 0, then starting from any extension like that, we get that omega nabla is of phi, for phi in the 0 form. So a homomorphism of aj with values in aj. Oh, I have no space left, but I can write it here. Then you can check that nabla minus phi is going to do it. Is going to be transversal. Okay, so I write it here. This is going to be transversal. And actually, I realized while preparing the talk that because I wrote, sorry, no, I cannot. I wrote define on leaf, but in that setting, it's not as clear as for other Atiyah classes. Basically, from the construction, you would want to say that if we started from a transversal connection as in step 2, then this form vanishes, but it only vanishes on flat sections. And a priori, we're not completely sure that they generate everything. So we need to be a bit careful, but later it will be okay for other settings. So that's the construction of the Atiyah class, at least how I construct it. It was defined, well, this Atiyah class of a leap pair was defined by Shen, Tieno, and Shu in, well, the paper was published in 2016. And there's a very nice paper from 2014, which is on the archive, which explains this Atiyah class of a leap pair as an obstruction to a Kaplan of DG manifold that is associated to the leap pair to be linearizable. So if you have questions about that, I can tell you later. But yeah, it's a very nice paper. I learned a lot while reading it, but I had the feeling, well, it sounds a little bit complicated. I mean, it's, yeah, it's very nice, but I will show you that there's a very simple geometric interpretation of the Atiyah class of a leap pair as an obstruction to the leap pair carrying more structure, so more, in a sense, reduction data for the subalgebraic. Okay, so just to convince you that these ideal systems, infinitesimal ideal systems, I will talk about as I was looking at. Yeah.
Can you say again, what does it mean for the connection to be transversal?
Transversal is this condition here. So in the context of a foliation, it's a connection that sends projectable vector fields to projectable vector fields. So the connection itself induces a connection on the quotient manifold if it exists. Okay, but just for a leap pair, you just define it algebraically like that. So if you have two flat sections under the bot connection, they are sent to a flat section under the bot connection. Yeah, so in a sense, for that, I needed this connection, this A connection on A. Yeah.
And is there a natural extension that you're trying to, that you can view the Atiyah class as giving you the extension class?
The extension class, what do you mean with the extension class?
Like an extension of A mod J by endomorphisms of A mod J. Like
yeah, they must be related. No, I'm not sure what you mean. I'm thinking about the case of principal bundles. but that's probably not what you want. Yeah, I don't know. Let's discuss it afterwards. Right. So let's look at holomorphic vector bundles. I wanted to say much more about that, but actually there's not much time. So I've reduced it a lot.
Well, don't worry too much about the time. Like, we are very flexible. Like, you should count for 1 hour without interruptions.
Yeah. Well, yeah, that's why I reduced that time. So just recall the complex manifold. Let's say it's a smooth manifold with a holomorphic atlas. So you have change of, so your manifold is even dimensional, and you have an atlas with change of charts that are holomorphic or biholomorphic maps when you identify R2M with CM. And then on a complex manifold, we want to consider holomorphic vector bundles. So they are not only complex vector bundles. A complex vector bundle is a smooth vector bundle with complex linear fibers, but we want as well to have a holomorphic structure on the vector bundle as a manifold, such that the projection is holomorphic and such that the local trivializations are holomorphic, right? So bear in mind that a complex vector bundle is not a holomorphic vector bundle. A holomorphic vector bundle is much more than that. But there's a nice definition which I attribute to Kobayashi because I found it in his book. I'm not sure whom this is due to. So you can say a holomorphic vector bundle, well, a complex vector bundle can be made holomorphic or is holomorphic if it carries a C-linear connection. So C-linear means C-linear in the second argument. Of the complexification of the tangent bundle of M. So you have J, let's call it J, is the complex structure on TM. It's a multiplication by I in the fiber that you get from your complex structure on M. When you complexify TM, you can complexify this map as well. And you get the two eigenspaces, T10M plus T01M of to the eigenvalues I and minus I of this complexification. And yeah, so T10M is isomorphic as a complex vector bundle to TM. And you can show that if there's a C-linear connection on this space and on E, such that its restriction to the second space, so the D01, is flat, then you have a holomorphic vector bundle. And how do you do that? Well, you say that the flat sections are the holomorphic sections, right? And then D01 is just a del bar operator. Del bar operator of your holomorphic vector bundle, you say, or you find that del bar of a section E is 0 if and only if E is holomorphic. And in this context, I'm of course only talking about local sections, right? So again, we have flat sections, and we have a flat connection of a Lie pair. I mean, we have T01M, TMC is a Lie pair. And this time, the subalgebroid acts flatly on another vector bundle, but the flat sections are again very geometric. I mean, they are the holomorphic sections. So then, Atiyah's construction is about the existence of a C-linear connection so TM connection on E that is holomorphic. What does that mean? It means that it sends holomorphic vector field. Again, I should put U here, so I should put U. So local holomorphic vector field on M and a local holomorphic section of E to a holomorphic section. And that's really not given for a holomorphic vector bundle. In general, you will not find such a connection. But if you think a little bit about it, we can again extend this connection, or somehow I think it makes more sense to identify Tm with T10M and to extend it by the del bar operator on the second argument. So we get TMC E, and we have this connection. And what we're really asking, what we're really asking is for X, I should say a section of T10M del bar flat, where here is the del bar operator of the holomorphic structure on Tm, the tangent of the manifold, and E in gamma E del bar flat, we want again, we want dXe to be del bar flat, right? Because del bar flat means holomorphic. So we are really in the same situation as before. We have a leap pair, we have an action of the subalgebroid on another vector bundle. Well, it's a similar situation, just that E is not Tm or TMC. But it's a very similar situation. Flat sections need to be sent to flat sections, right? Just this time, flatness means holomorphic. In the case of a foliation, flatness meant projectable. And so with the same construction as before, we get the Atiyah class of E, which is, sorry, not an omega, but cohomology class in T01M with values in Hom, T10M, and E. And it's the Atiyah class of the holomorphic vector bundle E. And well, what Atiyah, why you define it is it vanishes if and only if there exists a holomorphic connection, right? And the construction is really as before. If it vanishes, then well, any connection will be this curvature form I define is D over Hom, and then you correct it and you get your holomorphic connection. Okay, so we have a very similar situation. That's the original Atiyah class, and but we notice that this time it's really a leap pair acting on something else, right? So it's not an Atiyah class of a leap pair unless E is itself Tm, right? E is a holomorphic tangent bundle of M. And I'm going to show you how that actually is a situation of the Atiyah class of an ideal, actually, of an ideal in a Lie algebroid. And because I promised in the abstract, I should say, so before the Atiyah class of a leap pair, well, that was the one due to Shen, Sieno, and Shu. In the case of the foliations, that's what I call the Molino's Atiyah class in the abstract. So in the case of the foliation, it's also called Molino class. Okay, so in order to see this as the Atiyah class of an ideal, I'm going to look at a particular situation. We're going to forget about the Atiyah class, just the structure objects. We assume now that our holomorphic vector bundle is now called A, and it's a Lie algebroid, and it's a holomorphic Lie algebroid, which means that let's say as a smooth vector bundle, it carries a Lie algebroid structure, but this Lie algebroid structure sends holomorphic sections to the bracket sends holomorphic sections to holomorphic sections, and holomorphic and the anchor sends holomorphic sections to holomorphic vector fields. In that case, we still have TMC is T01 plus T10. So we have these two involutive subbundles of TMC, and we're going to complexify A as well and write it as A10 plus A01, where these are now the eigenspaces of the multiplication by J in the fibers of A, but then complexified. In that case, we're going to see the del bar operator, the T01M connection on A, but then we identify A with A10. That works even linearly. And we're going to note that A10 is actually AC modeled by A01. So we have that. And then we think a little bit about it. Well, that condition here means that if A and B in gamma A are holomorphic, so are del bar flat, maybe let me put A10 here, then also AB. That also gives us that if A, sorry, my screen is not liking my pen at the moment. Right, so if a section of A10 is nabla flat, that's a little bit more work to see it, but I mean, it's maybe 2 lines instead of 1. You can check then that AB is a section of A01 for all B in A01. That's actually pretty standard. And then the second condition tells us, first of all, the complexification of the anchor needs to send A01 to T01M. And finally, it tells us that if A in gamma A10 is nabla bar flat, so it's holomorphic, then the anchor is holomorphic, so it's del bar flat for the del bar operator on the holomorphic tangent bundle of M, right? And so we have all these properties, and we recover properties that we had before for the foliation. We had that flat sections bracket into flat sections. Flat sections, here we have an ideal condition again. Flat sections bracket the whole of A01 into A01. And then we have, in addition, a new compatibility with the anchor that we couldn't see before. But in any case, I'm going to show you a definition in a moment, and you're going to see that we can say that T01M, A01, and the del bar operator is an infinitesimal ideal system, let's say, infinitesimal ideal system in the complexified Lie algebroid AC. Right, so just to make sure that the next definition is motivated, keep in mind a holomorphic Lie algebroid is just an infinitesimal ideal system in a complex Lie algebroid, okay, over a complex manifold. Okay, mine's right. So now I can finally give you this definition. I hope it's motivated enough. So it appears in a paper by Hawkins of 2007, groupoid approach to quantization. And it appears under this name in a paper of myself and Christian Ortiz as an infinitesimal description of multiplicative foliations on groupoids. And Marius, Maria, Salazar, and Ivan, they're all here. They also found a structure in one of their papers around the same time, but in a setting where this Fm here is a whole of Tm. So I'm going to explain, to go through that definition. So you start with a Lie algebroid, and you consider a triple. So you consider a triple. Let's start with the middle. You take a sub-algebroid of A. So actually, you start from a Lie pair, AJ, with a Lie pair, and you ask for a subbundle of Tm, Fm, which anchors J, and you ask for a flat FM connection on A mod J. So it sounds like a lot, but I'm going to explain it in a minute. These three objects need to satisfy conditions. So the first condition is an ideal condition, as we had in our examples. Flat sections under this connection must bracket the whole of J into J. So that flat sections satisfy an ideal condition for J. J is just a subalgebroid, but there's somehow some ideal structure. And then the two other conditions, they are not in blue because they are somehow less important. I mean, they are as important, but their strengths may be, I mean, they are maybe, what do you say? Yeah, they are somehow less important, let's say. Why? Because, for instance, if rho of J is Fm, so if Fm is really the whole, I mean, if rho sends J surjectively to Fm, then those two conditions are just following from one with the Jacobi identity. That's quite easy to see. So in that sense, they have a less important flavor. Also, if you think about this example, I leave it as an exercise maybe, but if you take a Lie algebroid over a point, then the only thing that's going to remain is the subalgebroid of the subalgebra of the Lie algebra, right? Because Fm is going to be trivial because M is just a point. The connection is going to be trivial, and 2 and 3 are also going to be trivially satisfied. The only thing that will remain is 1, which is just the ideal condition. Elements of I and elements of your Lie algebra need to bracket into I. So that's really the ideal condition, and you can rephrase it as something that is less striking if you come from the point of view of Lie algebroids, but that gives you a really good intuition of what this structure is. That's just equivalent to nabla J, so for any section J of J, for any section A of A, that's really equivalent to saying that the bot connection is just this representation, but I mean the pullback of this representation under the anchor, right? So a priori, you start just from a Lie algebroid and a subalgebroid, and you want to know, you want to understand this bot connection. I'm going to show you that if you have all the structures, so if you manage to anchor J into a subbundle or subalgebroid of Tm, and if you find a flat Fm connection on J that does this, then your bot connection has become geometric, and somehow it has immediately a really concrete sense that I'm going to explain. So just before we move on, I'm going to say, so if I find those objects, Fm and nabla, I'm going to say that AJ is an infinitesimal ideal pair. But in the talk, I'm going to call those triples simply infinitesimal ideals. In the literature, they are called infinitesimal ideal systems. So remember, we have naive ideals. They are the subalgebroids which have trivial bot connection. And now we have those infinitesimal ideals. And really the geometric intuition for those infinitesimal ideals is that if you're lucky, you will be able, well, you'll always be able to take A mod J as a vector bundle over M. But if J is not an ideal, I mean, the sections of J are not an ideal in the Lie algebra of sections of A, that will not have a Lie algebraic structure, right? No chance, except if you have a naive ideal. But what the infinitesimal ideal system does is actually quotienting that by parallel transport along the leaves of Fm, so that if you're really lucky, you get a new vector bundle over M mod Fm, right? And I say lucky because first of all, this leaf space needs to be a manifold, and here there's a holonomic condition. You're not completely sure, even if things are smooth, that you get a vector bundle structure. But let's say, just for the motivation, if you're lucky, the ideal system is reduction data for a Lie algebroid, just as the foliation is reduction data for the tangent bundle. And then then of course you have your projections and you have a fibration of Lie algebroids. So that's really if we are lucky. In that case, and that's a theorem by Christian Atiyah and myself in that paper. In that case, the infinitesimal ideal system integrates to an ideal system in the sense of Mackenzie and Higgins. I'm not going to define ideal systems. Just keep it in mind as a semi-global version of that, or just as an infinitesimal ideal system for which this quotient exists and is a Lie algebroid. So in that case, Fm J nabla is an ideal system in the sense of Mackenzie and Higgins. And that's really why our objects are called infinitesimal ideal systems. Okay, so in that case, we have this construction and the connection, the connection really tells us which sections of A project to a section of the quotient. So nabla tells us which sections of A project to sections of A bar. And even so as before, even if this quotient doesn't exist, you should think about this this connection in this triple as single out special sections that want to be projected. Okay, so then what did I want to say? Right, then we can consider again an Atiyah class. Really the same construction as before. I'm writing nabla I this time for the ideal condition, ideal connection, just to differentiate it from its extension. So we are going to want to find an extension of this ideal condition. Remember, nabla I is an Fm connection on A mod J. And again, as in the foliation case, as in the holomorphic case, we want a connection that preserves flatness. So flat section of the Lie algebroid, A bar, and a flat vector field, so projectable vector field, need to be sent to a flat section of A, right? So again, we have a condition like that, which again is called transversality. And this time with the same construction as before, we can define a class that is going to vanish if we have this condition. And conversely, we can always define a class as a restriction of the curvature of an extension to sections of F and sections of T mod F that is going to vanish if and only if we have a transversal extension to our ideal condition. So I don't recall the construction, just think about the construction as before, but you replace some of the A's and J's with FM and TM. But what we can note is, as before, if that guy exists, so if we have a fibration of Lie algebroids, and if we have if we have a fibration of Lie algebroids, you can take any TM bar connection on A bar, and you can lift it to a TM connection on A that will have to be transversal to the ideal condition, and that will have to have vanishing Atiyah class. So as before, we have a theorem. So you start with an infinitesimal ideal system. If the quotient bundle, vector bundle exists, and really it has nothing to do with the Lie algebraic structure, then the Atiyah class of the infinitesimal ideal vanishes. Or in other words, if your infinitesimal ideal system is actually an ideal in the sense of Mackenzie and Higgins, then the Atiyah class must vanish. And then that brings us to our problem. If we start with a Lie pair, so if you start with, maybe I didn't write here. So if you start with J, a subalgebroid of A, well, it can be just a subalgebroid with no further structure, but you might want to ask yourself, does this subalgebroid have a chance to be the kernel of such a fibration, right? Because if I have a fibration like that, then really, sorry, not A, but J is the kernel of the fibration as a morphism of vector bundles. So a subalgebroid, but maybe if we look at the case of the algebras and subalgebras, if the subalgebra is the kernel of a morphism of the algebras, obviously it's automatically an ideal. But in the case of the algebroid, it's not necessarily the case. It's automatically a subalgebroid, and then you need to look at more structure, which is exactly this structure, the ideal system. So then if you turn your point of view, you start with a Lie pair, and you ask yourself, well, when is it an ideal pair, right? So I'm going to write, then I'm going to say that AJ is an ideal pair, because if you find a structure, J is much more than a subalgebroid. It's actually what should be called an ideal, but with this additional structure. So it's the fiber of an ideal. And the question I want to ask is, well, how do we see that AJ is an ideal pair? When do we see that, or how do we see that? Or, I mean, can we find an information? And the answer is, well, it's not if and only if, but the answer is, if the Atiyah class of the Lie pair vanishes, then you have a chance. If the Atiyah class of the Lie pair doesn't vanish, then there's no chance. J is not going to be the kernel of a fibration for any possible fibration of your of Lie algebroids. Okay, so that's what I want to show. Okay, so I said I would skip more, so I'm skipping, it was planned, you can always ask me later. So I'm skipping the foliated principal bundles. I just tell you, in that case, you have really nice families of ideal systems that work together. And we're just going to skip to go right away to the proof of the theorem I just said. So we start with a Lie pair, AJ, and we assume that we can anchor J into an involutive subbundle of Tm. And we assume that this involutive subbundle has a flat connection on A mod J, right? So it's really the first part, really the first part of this whole structure. Then if you have that, you can definitely define, I mean, the anchor definitely defines a well-defined map from the forms where this curvature, this Atiyah form for the ideal lives, to the forms where the Atiyah form for the Lie pair lived. And this map is just the anchor on almost everything except the last term. And then next step, if the connection that you found is really a geometrization of your bot connection, then this map becomes a chain map. So it's going to give you a map in cohomology. there's no need to prove that. I mean, it's really an easy exercise. It's just Jacobi and the curvature vanishing, the curvature of the bot connection and of the ideal connection vanishing. It's really very easy. And it's also very easy then to show that if you have an infinitesimal ideal structure in A, so with fiber J and with anchor Fm, then the image under this map, so under the anchor of the Atiyah class of the ideal is going to be the Atiyah class of the D pair. Again, that's very easy. You just need to start from an extension of the ideal connection. So you extend it to a TM connection on A, and then you realize that the pullback under the anchor is an extension of the bot connection, and then it's just writing it down. Then it's just writing the anchor and realizing that the anchor already this map sends the one curvature to the other one. Right, but then we're already done with our proof, because remember I said that if the infinitesimal ideal is an ideal, so if there's a vibration of the algebraics that's with kernel J, then the Atiyah class of the ideal vanishes, and then obviously its image under the anchor will have to vanish as well, right? So we get the theorem if you start with a Lie pair. If you know that AJ is an ideal pair, so in the sense of Mackenzie and Higgins, then the Atiyah class of the Lie pair vanishes, okay? And maybe, I mean, it's always more striking to say the converse. If the Atiyah class doesn't vanish, then J cannot be a kernel of a vibration. So it cannot carry an ideal structure. But I should say, be careful here. It's really about ideals in the sense of Higgins and Mackenzie, because if it would be infinitesimal ideals in general, so if a Lie pair, if the Atiyah class of a Lie pair would vanish as soon as you have an infinitesimal ideal with fiber J, then all Atiyah classes of foliations would have to vanish. All Molino's Atiyah classes, and that's not true, right? Because subalgebraics of tangent bundles all carry a canonical ideal structure, infinitesimal ideal structure. Okay, so that's where I stopped, but if you're interested in more examples, I can tell you anytime about principal foliations. I just give you a couple of references if you're interested in infinitesimal ideal systems and so on. So that's where we find them at Christian Ortiz and I find them as the infinitesimal description of foliations. Actually, I should add a reference. I forgot that. Then Marco Zambon and Shenchan Zhu described infinitesimal ideal systems as a special foliations on N manifold on Lie1 algebraics, so NQ manifolds of degree 1, which fits with that, because our ideals are actually also, they can be understood as just foliations on Lie algebraics, which are compatible with the Lie algebraic structure. Then in a later paper, we proved that infinitesimal ideals are sub-representations of the adjoint. So if you were not convinced until now, then you know it. I mean, they are what we call ideals in the context of the algebraic. Then what I talked about is already on the archive, but in a very bad shape, I realized. So there will be a new version very soon. There are other obstructions in terms of Pontryagin classes. That's in another paper. And if you're interested in holomorphic vector bundles and how, I mean, these ideal structures over there, that's in a motivation of a paper with Malte Heuer, which is also going to be ready very soon. So I stop here and I thank you for your attention.